Now, of course, in some cases, finding the derivative of a function may not be that easy. And Newton-Raphson method uses the derivative of a function. Now, indeed, we can approximate the derivative of a function in different ways, and we are going to see it in detail in the forthcoming lectures. So, at the moment, simply we can simply approximate a derivative by taking the differences between two values of the functions and divide it with the x coordinates. So then we can approximate the derivative of the function, and we can substitute f prime xi into the expression. As a result, we will obtain this expression. As you see, in this expression, I don't have any derivatives. I only need to evaluate the function 3 times, as you see, and then multiply it with the difference between xi minus 1 minus xi. Xi minus 1 is the x value in the previous iteration, and xi is the x value for the current one, and then we move to the new coordinate in which is possibly close to the root. Okay, so let's see how it works. We call this technique secant method, basically. Now, just assume that we have a point xi minus 1, and then we have the xi. We calculate the derivative of the function, and then we draw a straight line. This is the basic idea of the secant method, which passes from these two lines, and then we find the new point which crosses the x-axis. Now, this is my new function, and then I do something like this. I draw a new line, and then I find the new point which crosses the x-axis, and then it goes like this, and at each step I'm getting closer to the root of the function. This is what the secant method is. Now let's look at the convergence of different root finding methods. As you see here, this is the convergence of bisection method, and it needs approximately 20 iterations to reach to the true percent relative error. Okay, and let's see the number of iterations for other techniques. So you see, this is the false position method. Okay, the number of iterations. And secant method is here. You see, it needs more iteration compared to the Newton-Raphson. It follows more or less an identical path by means of error, but of course it needs more iterations for the same error. So let's draw a straight line here, and let's check the errors. For example, here this is the number of errors, number of iterations for the Newton-Raphson in order to reach the 10 to the power minus 4, and certainly the secant method needs a little bit more iterations, so which means that it is computationally more expensive compared to the Newton-Raphson method. You don't need to calculate the derivative, but that has a cost, and as a result you spend more time. You need more computing time, CPU time, in fact. And here we have the fixed point false point iteration, false position method, sorry, and of course almost you double the number of iterations compared to the second method, and the bisection method has much higher number of needs much higher number of iterations, so the CPU time is almost doubled compared to the false position method. Now how we can apply the second method in MATLAB. So again, this is our expression in Newton-Raphson method, and in the second method, as we have said, we just approximate the derivative by using backward differencing. Of course, you can use different techniques for approximating the derivative of a function at a point, but now just assume that we use backward differencing. So what is a backward differencing? We evaluate the function at a point before than that value, and then we calculate divide the distance between 2 points, and as a result we approximate the derivative, which gives us this expression. So simply the difference between the Newton-Raphson and the second method is in using the approximate derivative. Okay, now let's return back to our MATLAB script, which we have used in finding the root by using Newton-Raphson method. And let's say that, let's modify it, and let's say that this is the second, so we just modify it a little bit. Now instead of taking the derivative here, I will use approximate derivative. So this is the difference, and in fact for this purpose I need to calculate the value at the previous function, and therefore I have to, if I use the same value xr, so basically this will be 0 and this will generate an error. Okay, so what I need to do is I have to define something else for the previous value. I will move this line to here now. Just a moment. So I need the FR and FR previous, FR minus FR previous, divided by XR minus XR previous. So this is my DFR now. Okay, now from here I calculate the new XR, but here now I have to update my XR previous, and calculate the new XR. So here I need another line, FR previous, and that has to be equal to fr. Okay, so fr is assigned to fr previous. Now I evaluate xr with the fr. Yes. Now fr and fr previous is computed. So by finite differencing, now I will have a new xr and done. So let's go. Let's see whether there is an error or not. But in order to evaluate this function, we need an xr previous. So let's say that I will put in another line here. So I need to make an approximation for the xr previous. So let's say that this is 21. And then I will debug the code. I will put a breakpoint here. Okay, I set the breakpoint. That's okay. The code is run. Now the previous value is 21. Yes, xr is 20. Now continue. Index is equal to index plus 1. Fr previous is equal to fr, but we haven't set the fr previous. So we need a fr function here. It will break here. Yes. Okay. So this basically means that we have to switch we have to take these values outside the loop. So let's do it like this. That's also okay. This is okay. So I will evaluate the function just outside the loop for the first time. Now fr and fr previous are evaluated. That's also okay. Then what I need to do is I will need to evaluate the fr just here. Yes. Now let's check it. Now I have the xr previous for the first iteration, then index is increased, then I calculate the approximate derivative, then I set xr previous to xr, I update it. Now I updated the xr is revised, therefore I can calculate the xr previous to the fx previous. Then I need to calculate the fr, and then it goes like this. Then the rest of the lines are the same. I don't change them. I calculate the relative approximate percentage error, and I write it to an array. I write the root value to an array, and it continues until these two criteria are satisfied. And let's check it. I will run the script again. Okay, now I have the fr previous value. This is 8. That's also okay. I go one step further. That's also okay. Now let's see how the DFR is approximated. It's minus 1.27. FR is known now. And 13.44 is the first approximation, and I remove this breakpoint and I say that continue. And let's check. Okay. So the red line is the function, the actual value of the function, and the blue lines are the iterations. Whether I can catch the value here. Okay. From tools, I will zoom in. Yes. Or let's zoom in here. You see, again, identical to the Newton-Raphson method. Now, as you see, remember that the Newton-Raphson method reaches to the same amount of error by means of percentage in 5 iterations. Now we have 6 iterations in total for the second method, but we use an approximate derivative. Again, we have the degrees of relative approximate percentage error for the function. Okay, so this is one approach. It converts quite fastly, but of course you can play with it and you can make some changes. For example, instead of using the XR previous, you can use a step size, and you can increase the accuracy certainly in the second method.